Dr.M.G.R. Educational and Research Institute, University, Madurai, Chennai. Dr.M.G.R. Educational and Research Institute, University, Madurai, Chennai.
Good afternoon to one and all gathered here. Education is the most weapon which you can use to change the world. I hope those who have joined here today have chosen the path of learning. I am M.G.R. working as Assistant Professor, Department of Chemistry at Dr.M.G.R. Educational and Research Institute. It gives me immense pleasure in anchoring today's program, Nuclear Energy Working Principle and Safety Features of Kudankulam Nuclear Power Project by Dr. S. Anandan, Officer in Charge, Nuclear Information Center, Kudankulam Nuclear Power Project. So in this studio, we have our colleagues, Dr. R. Nitya, Mrs. Sasikala, Dr. R. Lavanya, and Mrs. Ganesh Babu, our system admin. Let us start this program by welcome address. I invite Mrs. M. Sasikala, Assistant Professor in the Department of Chemistry, to give welcome address.
Good afternoon to one and all connected here. I am M. Sasikala, Assistant Professor in the Department of Chemistry. It is my great privilege to propose a welcome address on behalf of Chemistry Department. I express my heartfelt gratitude to our beloved Founder Chancellor A.C. Shanmugam Sir and our Honorable President Engineer A.C.S. Arun Kumar Sir for encouraging and motivating us to conduct many number of online programs. I am also indebted to welcome our Vice Chancellor, Dr. S. Geeta Lakshmi, our respected Registrar, Provost, and other higher officials of our university. I am very much happy to welcome our Joint Registrar, Dr. S. Ramalingam, Dean Dr. S. Manivannan, who stands behind us in organizing fruitful events. I also take this opportunity to welcome our Deputy Dean Academic, Dr. A.R. Arunachalam, and Deputy Dean Administration, Professor K. Sendil Kumar, and Dr. S. Valliyamai, Head Department of Chemistry, who are always on their heels and keen enough to support and encourage their staff for conducting valuable program. I feel immensely happy in welcoming our today's chief guest, Dr. S. Anandan, Officers in Charge, Nuclear Information Center, Kudankulam Nuclear Power Project, Tirunelveli District, Tamil Nadu. He is a person who has rich experience in the working of nuclear reactor. I welcome you, sir, to deliver a talk on Nuclear Energy Working Principle and Safety Features of KKNPP. I think we all will be benefited in your valuable presentation today, sir. I welcome you once again, sir. A pleasant and a very warm welcome to all the participants, without whom this program could have not been successful. I also welcome our department colleagues and thank Mr. Ganesh Babu, System Admin, who always render his helping hands in times of need to make this event a successful one. I welcome my dear students who are utilizing this opportunity for their success. Thank you, one and all.
Now I invite Dr. R. Nitya, Assistant Professor, Department of Chemistry, to introduce our chief guest.
Ma'am, unmute please. Ma'am, unmute பண்ணிட்டு please.
Madam, we must feel happy to have Dr. S. Anandan, an eminent personality among us for this webinar. I take delight in speaking a few lines on his achievements. Dr. S. Anandan is currently working as Scientific Officer E at Kudankulam Nuclear Power Project, KKNPP, Tirunelveli, Tamil Nadu. He is also engineering in charge in Nuclear Information Center, Kudankulam Nuclear Power Project. He has completed his doctorate degree in mechanical engineering and has published many papers related to nuclear power projects. He has received NPCIL Group Achievement Award from KKNPP for the year 2009 for passive heat removal system, structural and design work, and for the year 2011 for the public awareness initiatives. Regarding his profile, he has totally 35 years of experience in the field of atomic energy. He has also worked in Narora Atomic Power Station, UP, Gaiga Generating Station, Karnataka, Rajasthan Atomic Power Station, and in Baba Atomic Research Center, Mumbai. He has another feather on his crown. He was also deputed to Moscow, Russia, as a material inspection specialist from KKNPP for 1 year during 2014 to 2015, and he has proved his mettle and returned after completing the project. We are happy to invite such an eminent personality to this webinar to deliver his valuable speech on nuclear energy working principle and safety features of KKNPP. We welcome you, sir.
Thank you, ma'am. There is an announcement to the participants. You can post your queries in the chat box, which will be answered at the end of the session. You can receive your e-certificate after submitting the Google form, which will be available at the end of the session. Now I invite our chief guest to deliver his valuable talk.
Good afternoon.
Yes, sir. You can continue.
Respected Dean, have you heard the voice?
Yes, sir. Yes, sir. You are audible.
Okay, let us continue. Respected Dean and Deputy Dean of Dr.M.G.R. Educational and Research Institute, HOD of Chemistry and all faculties of Chemistry Department and all other dignitaries of this institution, and my dear students and lecturers, good afternoon. Myself is ANANDAN, working at Kudankulam Nuclear Power Project. Today, I am going to deliver a webinar on nuclear energy working principle and safety features of KKNPP. Detailed PPT is going to present today about this topic. Friends, first of all, let us know something about the electrical energy scenario. We all know that the electricity is very much important as on today. Energy becomes the major criteria for the development of a country. The governments in the most of the nations are concentrated on self-sufficiency electricity of their own. Electricity generation at present conditions, mostly from fossil fuels, account for 33% of the carbon entering at the atmosphere annually. Fossil fuels are non-renewable and their use releases carbon into the atmosphere with consequences that are causing concern. Renewable energy sources, wind, wave, tidal, solar, hydro, geothermal, can realistically provide only fraction of energy we use today, and a smaller fraction of much larger demand for energy that is predicted for 20 years from now. Nuclear power offers a great promise in helping to reduce greenhouse gas emissions and also supplementing the energy supply to meet increased future demand. In view of its vast energy potential and compelling merits, there has been renewed global interest in nuclear power. This arises from balancing the concerns for global climate change with the need of provide sufficient electricity at an affordable cost for the growing global population. There are different types of electricity production. For example, thermal, hydro, wind, solar, nuclear, etc. Let us understand What is current? We all know that the flow of electron called current and the law of electricity derived by Michael Faraday. The equipment which produced electricity is called the generator. Generator is connected with the turbine shaft and both rotates together, then electricity produced based on the law of electricity. So, first of all, I welcome to explain this PPT. Now, I am going to tell you what you are seeing. This is the two huge monument of our great India's nuclear highest power production in India. Each, you have seen unit 1 and 2, each unit producing 1000 megawatt, and at present in Kudankulam, we are running these 2 units and 2 more units. Kudankulam 3 and 4 is also construction is going on, and 5 and 6 also we got approval. So at Kudankulam, almost we are near future, 5 to 6 years after, we are able to make 6000 megawatt. Just imagine it. At present, our Tamil Nadu total requirement is around 12,000 megawatt only, out of which nearly 50% of electricity is coming from Kudankulam. Then the future of Kudankulam is well bright. Friends, just we can see the electrical energy mix in India. There are fossil, renewable and nuclear. So fossil, as we know that coal, gas, oil called fossil. Renewable source, again category by 2, hydroelectric and others wind, solar, tidal and geothermal. Then third one is nuclear resources. There are 2 types of nuclear resources. One is fission, 3-stage nuclear program, and fusion is another method. Now let us concentrate. I already told you thermal and nuclear both are producing the steam to rotate the turbine. As I already told you, that generator where the electricity has been generated, the generator has 2 main parts. One is rotor, another one is stator. Rotor is a rotating part, stator is a stationary part. Both are coil winded. When the rotor is rotating such a specific speed, the EMF, the electromagnetic force, will induce. When we cut with the flux, the current will produce. This is the theory, this is the law. Based on that only, every way of electricity is producing except solar. Because solar is a photovoltaic cell. From the sun rays, it reflects there, and then the flow of electron took place. That is why it is called current. It has been saved through battery or to the connect to the grid. So here in the thermal and nuclear, we are using steam to rotate the turbine. So how to produce the steam is the main cause, the name of it. Here the left hand side, you are seeing that coal or oil or natural gas, where the boiler, below the boiler, we put coal and burn the coal. The boiling water is getting steam. Sorry. The steam is going to turbine, and then it rotates the generator where the electricity has been generated. Again, the outside, the last stage of turbine blade, the exhaust steams, again cooled by the seawater, then it again back. So that is a one closed cycle. Here in the right side, if you see the nuclear powers, this also same except the secondary side, but in the primary side, instead of the coal and boiler, we are making one reactor building where we can keep the reactor vessel and where we can use the uranium as a pellet. When the uranium hit with the neutron hit with the uranium, then the uranium will again split into xenon, krypton, boron, something else. Then it releases a lot of heat energy. If one uranium atom split, it releases 200 million electric volt. So that heat has been taken away through the water, and then it will go to steam generator where the blue color steam generator is there. There the water is there. That water becomes steam. That steam will go to turbine, rotate the turbine. We are getting electricity. Okay, this is the 2 different size. If just the primary, if you close it, if I close the primary of these 2, thermal, nuclear, the remaining, the secondary, both are same. So except how to produce the steam is differ from this thermal and nuclear. Okay, then if we go the further deep in the nuclear power plant, you see the left hand side one containment structure is there. That is what we are calling is the reactor building. There some reactor vessel is there. Inside that red color water is circulating, where we can keep the fuel rods there. And then when the fission took place, lot of heat has been produced. As I already told you, that heat has been taken through the primary heat transfer system, that is RCP, reactor coolant pump. That heat has been taken, carry away, and then hot water will go to the steam generator. There the DM water, demineralized water will be there. That water will become steam. That steam will go to turbine, and rotate the turbine, we will get the electricity. Okay, so after completing the work, the steam, we should not waste it. We should not, you have to utilize the efficiency. So we are using the third stage condenser. We are using the seawater to cool the steam and then go back. Okay, this is the very, very simplified diagram I have shown you about the nuclear power plant, especially for the Kudankulam nuclear power project. Okay, let us also just think the India's electricity mix. You see, at present, nearly 3 lakh megawatt has been produced by our Indian electricity, out of which the thermal is nearly 60 to 70%. We are making through thermal. Next one is hydro, around 16%. Then renewable energy 12%. Then nuclear at present 2%. Okay, this is the India's electrical mix as of now. And then our future forecast, because this whatever the electricity has been produced, that is not sufficient for us to improve the to construct more and more power plant in all the by all means. So our future forecast by 2032, our government has decided that to increase the thermal, but because you see here the thermal percentage has been slightly come down 70 to 56. That is different because that we have to increase the other things. We have to increase 16 to 21% by hydro and 12 to 14% by renewable and 2 to 9% by nuclear. This is the total 7 lakh megawatt we are planning for 2032. Okay. One more thing you have to see, the coal and the gas and these two, CO2 emission is high during the electricity production. You may see that nowadays the global warming has been taken place and carbon emission is also highly talked by the global standards. So just I have shown the equivalent by kilowatt hour. The coal is highest, nearly touching 1000, but directly and around 289 by indirect from life cycle. As well as you just see that hydro, solar, wind and nuclear, there is no direct emission from this. There may be some indirect from life cycle, hydro and solar is there. Still nuclear is totally free from CO2 emissions. Then cost. Next thing we have to think about the cost comparison of electricity in different types. You see here also high. The coal is slightly moderate because the minimum cost of this one 2 rupees 79 paise per unit, whereas highest is 5 rupees 29 paise. Compared to the coal, the natural gas is 266 to 10.67, and diesel and naphthalene is touching about 13.01, whereas nuclear energy 95 paise per unit to 3 rupees 90 paise per unit. Okay, the hydro is also 0.86, 86 paise to 5 rupees 77. When wind energy is 374 to 6 rupees, whereas solar is 722 to 1188. So this is per unit cost what we are talking about at present. It may be slightly down here and there. Okay. One more thing you have to see from this particular slide, I will tell you, the left hand side 1 spoon, you are seeing 1 gram of uranium, and right hand side you see 15,000 kilogram of coal. Both will produce 1 megawatt day power. Can you imagine it? Just think of it. So 1 gram of uranium 235 gives 1 megawatt day power. The same 1 megawatt day power, if you want to produce through coal, you have to burn 15,000 kg of coal. Okay, just you see the below one, annual fuel requirement for 1000 megawatt per year. If we are running in unit 1, 1000 megawatt per year, we need only 130 ton. That means 1 truck uranium is sufficient. Whereas if I want to use the same by coal, then 2000 trains, and each train will have 1300 ton each. So you just imagine it, how much coal, how much CO2 emission will come into earth. That one is, sir, how it is possible? You maybe ask me. Because it is that just you see these two pictures, you can able to find it. The left side you see the energy released per carbon. Or if 1 carbon atom release the energy, it releases 12 electric volt. Whereas 1 uranium atom, if I hit 1 uranium atom, it releases 200 million electric volt. That is why 1 gram of uranium will give 1 megawatt day power. Okay, sir. Next, you see, this is the RPV. This is the heart of the reactor, what we are telling that. So this is where we are keeping all the fuels inside this RPV, reactor pressure vessel. Okay, you see the right hand side, I put control rod. Just to control the fission reaction, boron, cadmium. These control rods is just top of the fuel. Next one is coolant. You may see the inlet, the blue color is inlet and the red color is outlet. 2 inlet, 4 inlet, 4 outlet will be there in this RPV. Then moderator, the slow down the neutron, cause fission, light water we are using here as a moderator. Then the total equipment called a reactor vessel, and the fuel assembly you see, that also I have shown, the uranium-235. Before we are thinking that the nuclear, just to understand about the nuclear, let us ask, what is atom? Can we know that it is the smallest particle, the matter of tiny particle called atom? We have studied in our 10 and 12 standard. So the atom has proton, neutron, electron, and we know that the number of proton percent the atom is atomic number. The number of proton plus neutron is called atomic weight, and same atomic number, different mass number called isotope. Okay, just these three, if you are able to understand, the nuclear theory is very, very easy to understand by this. Because the uranium we are getting from earth at present. Okay, in India we have the Jaduguda, where the nuclear mines are there. From there we are getting the uranium ores. From there the uranium ores has been processed and we are making the uranium-235 pellets. That is called the UO2. That means uranium oxide. That will be kept in the zircaloy tube. We build it, and then this zircaloy tube has been kept in the reactor core, and we are making it is a controlled fission. So during this controlled fission, as I already told you, that neutron hit the uranium atom, uranium-235, 92. That means 92 is proton, 235 is the total uranium weights. Okay, so the 92 uranium-235 plus 1 neutron gives xenon krypton plus 2.5 neutron. Okay, plus lot of heat energy and plus small amount of radiation. This is a chemical formula for that uranium-235 atom hit with the neutron. Here, what I told you, you just leave it that byproducts, xenon krypton, whatever that may be, it may be differ from the different equations, but we have to think of that heat, 200 million electric volt heat. That heat has been taken away through the water, and then one more thing is coming out, 2.5 neutron is coming out, out of which 1 neutron hit the another atom, so on continuing. That is called the chain reaction. We have to maintain the chain reaction. That is why the extra 1.5 neutron has been absorbed by the boron. Boron is the element which have the tendency to absorb the neutron. Okay, so the boron rods we kept. I already told you now. You see this picture, control rods. That is boron rods. So that we are controlling it from up and down, and we are allowing always 1 neutron available to maintain the chain reaction. Okay, this is what we are doing here. Okay, the next one, you see whatever I told you, RPV. The left side you see the uranium fuel assembly, that is, which we are calling the fuel assembly. It has the fuel rods together. It's a hexagonal pattern. There are 331 fuel rods put together, combined one fuel assembly. The right side you see, this is the inner side. There's the inner side, right side. That is a 163 fuel assembly, which this will be kept inside. And then we have to put top, close it, and then we are maintaining the fission process. Okay, as you know that the reactor under operation so far in the world, you see here I give you the brief about the world nuclear reactors. So there are 439 reactors in the world. Okay, out of India also you can see, find India is 21, at present 21, 22 is there now. So and United States of America has 99 reactors. So 439 reactors are there in this at present. And one thing I want to tell you, my dear friends, so the Kudankulam Nuclear Power Project, the KKNPP Unit 1 and 2 is coming under the category of Generation 3 plus reactor. What do you mean by Generation 3 plus reactor? Means it has the more passive, less active. What do you mean by passive and active? You know that active means it requires the electrical pneumatic support to operate it. Passive means which need not require the electrical pneumatic. That means fully automatic. So as we know that this passive system, that is the latest technology, Generation 3 plus reactors. So we proudly say that out of these 439 reactors, Kudankulam is the one of the best reactor in the world. Okay, in the future, this is a 3-stage reactor. One thing I want to tell you, my friends, sir, you told that there are different types of producing the electricity. Why we need nuclear? Why you are giving more important for this? Friends, for this I am telling you already, I told you, the solar, wind and hydro, which is called the renewable energy, it is limited. These type of electricity have some limitations. And I already told you thermal power station is a carbon emission thing. And nowadays the world just think of the nuclear. You see, what are the limitations in other source of renewable energy? You see, the solar is a very good energy. There is every way of electricity is good. I am not demeriting other source of energy. Just I want to tell you the truth that the solar energy is a very good energy. But the limitation of solar is that night we cannot produce the electricity. Only daytime, around 10 to 12 hours only we can produce the electricity. That is the one limitation of solar. Okay. And if you see the windmill, that is also, you cannot produce the windmill all the 24 hours into 365 days. Because, and even wherever you want, you cannot put the windmill. Because there is a 30 to 50 meter height. There is a wind flow will be, velocity will be there more than 50 kilometers per hour. Then only we can put the windmill. So you can find in Tirunelveli, Coimbatore, Tenkasi, somewhere else, some particular 2-3 places only you can see the windmills. You cannot see all over the Tamil Nadu. You cannot see all over the India. That is the wind requirement is there. That also not all the 12 months. It will be around 4 to 5 months. Okay. So that limitation is there. You cannot produce the full 365 days. This the efficiency capacity is less than 20% for solar and wind. Okay. Hydro. You see, the hydro plant will run when the rain comes and the dam will fill the water. Okay. All the 365 we are not getting there. All the 365 dam will not be filled. We already know that. We are already shortage of drinking water itself. So that is wherever the water availability is there, wherever the dam is there, already India is already set up the dam power plants, the hydro power plants. So what I mean to say, there are all very good energies. All the energies are very good. But now we have to go for the higher and higher production. For that, the need of nuclear is also one of the method. Here, I told you the 3-stage program. The 3-stage, the stage 1 is what I already told you. Uranium-235. I told you that uranium-2, when you get the uranium ore from the mines, you are getting the combination of uranium-234, 35 and 238. And out of which the 235 is only 0.7%. And the uranium-238 will be 99.3%. So that only we are keeping in this reactor, and uranium-235 only the fission atom, that only participate in the fission, that only split, that only gives xenon-krypton balance, that only gives heat, that only release small amount of radiation. Understand? So the remaining 99.3%, what is the uranium-238, that will simply absorb one neutron, and after 2-3 changes, it become plutonium. That is why we are seeing this stage 1. So this 99.3% fuel is not a waste. That is going to the plutonium. When it becomes plutonium, then it is a fuel for the fast breeder reactor. Next FBR, you are seeing the middle of that stage 2, where we are using in Kalpakam, we are using the Bhavani reactor. That is a fast breeder reactor, and already the research reactor is successful. Now the commissioning is going on. Here, what we are doing, we are keeping plutonium as a fuel in second stage, and we are keeping outside blanket as a thorium. Thorium, you already know that 90 TH 232. Okay, that is thorium. So this thorium, when we kept as the blanket, during the fission of this fast breeder, that thorium will absorb one neutron, become after 2-3 stages, it become 233. 233 is nothing but called artificial uranium. Uranium-233 you will not find in nature. So during this type of things only, you are getting artificial uranium, uranium-233. My friends, then come back to the third stage, uranium-233 fueled reactors. Here what you see, it is a breeder reactor. Here, if we put thorium converter to uranium-233, you put uranium-233 in the thing, outside you kept thorium, again and again it will be breeded. So what I mean to say, why we all do this stage 1, stage 2, stage 3? That means, friends, if once we make this stage 3 reactor into commercial, because the thorium availability in India is nearly 50% in the world available. That means whatever the thorium available in the world, out of which 50% available in India. So if we make these thorium converter reactors thorium based, that means breeder reactors, we can produce 5 lakh megawatt for 500 years. As I already in my beginning stage, I told you at present, put all together, we are producing only around 3 lakh megawatt. Okay, once this stage 3 achieved commercially, only through thorium converter reactors, we can make 5 lakh megawatt, not 1 or 2 years, up to 500 years. That much available of thorium in India. That's what I told you. Okay, this one important thing, when our Kudankulam 2006, our respected APJ Abdul Kalam sir came into our Kudankulam, he told this particular slide, he told that I want to see the stage 3 reactors at the earliest. So we also assured that we'll do our best at the earliest, sir, like that. So next one is, this is the Kudankulam reactor cut view. You see here the center one, the blue color you see, that is the RPV, reactor pressure vessel. Okay, and then left side gray color tanks you can see, that is the steam generator where the water will become to steam. Okay, then below the RPV you see that one red color thing, that is called core catcher. Okay, then you see the right side one green color tank, that is pressurizer. On the top of that you can see the polar crane, and then out of its inner containment, that outer containment. Okay, and then PHRS, the left hand side you see that is a top one dome structure. Okay, these are all the important equipment which we are using in Kudankulam. Okay, so out of which, these are safety things. What I mean to say, you see the safety, the center point of the reactor, So this is the RPV. Here only the fission will took place. Okay, here only the fission took place. Here only we can keep the fuel rods. When the fission took place, the heat has been produced. That heat has been taken away from this red color one. It will go to SG, and then it will release the heat. The tube side, cell side, the DM water will be there. That DM water becomes steam. That steam will go to turbine. Okay, after completing work, again it will come back to here. Then through the RCP, reactor coolant pump, again it will go back. This is the one closed cycle. There are 4 RCP, 4 SG is there. Okay, so next one you see here, this is the inner containment wall. This inner containment wall has the 1.2 meter thickness. PSS, that means pre-stressed concrete. Okay, then we have the 2.2 meter gap is there, and then we have the outer containment of this. This one is 600 centimeter. Okay, so apart from that, we are having the PHRS. This is the passive heat removal system. There are safety features. I will tell you what are the safety systems. One is that plant is running. Normally, plant will run as it is, whatever I already told you. And whenever any changes comes or any class power supply comes, then immediately the control rods will go down due to gravity, and then it will absorb the nearby neutron. Neutron will not available to maintain the chain reaction. The chain reaction will get break. The plant will get shut down. This is the shutdown system of this one. And furthermore, this will happen within 4 seconds. If any one of the rod or any bunch of the rod not gone inside, then immediately QBA second system, quick boron injection system will actuate, and within 20 seconds the plant will get shut down. Okay, to make, you see here this, I told you 4 RCPs are there, and everything will be running in same this one. And here the maintain the pressure is the very important thing, because as I told that the inlet temperature of this RCP to reactor, it is 299 degrees centigrade of 290 degrees centigrade of water, whereas the outlet temperature will be 321 degrees centigrade of water. As we already know that the boiling temperature of the water will be 100 at the atmospheric pressure. If you increase the pressure, you can increase the temperature in the water state. That is the one more law. So based on this, here we are maintaining the 15.6 megapascal pressure. That means nearly 156 kg of pressure. So how to maintain the pressure? Here we are using the third stage hot leg. We are keeping the pressurizer. Pressurizer will have the spray system as well as the heater system. That one pipe connection always will be there. If pressure increase, then spray will actuate and pressure will be decreased. When then pressure decrease, then heater will be actuate and then pressure will be maintained. So that is also one more systems we are using. And then apart from that, we are having this is ECCAS. That means emergency core cooling systems. Emergency core cooling system means there is a hydro accumulator, what we are telling. Any puncture happened in the pipelines, that what the design based accident, what we are telling. small loca, big loca, like the loss of coolant accidents comes. That time to maintain the coolant in this RPV, we are using the 12 lakh liter of water in this 31.7 meter elevation. This water will be directly go to our reactor pressure vessel by gravity. So this one more system. Apart from that, there are 154 hydro accumulators has been kept in the different areas of the RPV. Okay, reactor. So this this one, what will happen? This is one more safety of this system. Okay, finally we can say the PHRS, passive heat removal system. Passive heat removal system is a beyond design based accidents. As I already told you, 154 hydrogen recombiners in every places. That hydrogen recombiners have the TiO3, okay, titanium oxide. This TiO3, when the hydrogen forms during the fission, that hydrogen and this TiO3 oxygen will combine together and make water pillars and droplet in these particular floors. To maintain the hydrogen percentage within the safety level, we are using this hydrogen recombiners. Okay, for the next one is the precise PHRS, passive heat removal system. This system will actuate during the beyond design based accidents, because everything gone out, the station blackout conditions. At time we have to reduce the heat of this RPV. So when from SG, one point is there to go to this PHRS point. There the natural air will be cooled to the PHRS heat, and hot air will go to top. Hot air will go to top, and this again the steam will go to steam generator. This happened thermosiphoning method by 24 hours. This is one more safety. There are a lot of safety systems. Apart from that, I told you the inner containment wall. This inner containment wall has the 1.2 meter thickness and 6 mm carbon steel inside total light. It will be stopped by the biological shield of the radiations. It will not allow any radiation go outside the reactor building. And then one more, in between inner containment, outer containment, we are having the envelope space, which we are maintaining the pressure below the atmospheric pressure. So after this, there are 600 centimeter outer containment wall. This will be stopped by the external threats. So these are all the safeties we are using in this view. You see, that's what I told you. The PHRS area of the civil construction. When we construct it, this is the one. There are 12 heat exchangers is there peripherically. Okay. When the blackout condition, the steam will come to this heat exchanger. Inside heat exchanger will be there. That heat has been taken away by this atmospheric air. The hot air will go on top, and then system will be actuated within the heat. That will, you see here, I told you, when the plant is running, this will be happening. When the plant is running, the steam will go to turbine, rotate the turbine is connected with the generator, it will rotate, plant will get power. Okay. After that one, it will complete it. When the blackout condition, what will happen? Here it will be cut, and then this SG, the steam generator, steam will go to SG, PHRS checks, and then atmospheric air will take the heat, the hotter air will go to top, and then by this thermosiphoning, continuously thermosiphoning, this heat has been taken away by this steam generator. Okay, so there is no radiation will go to site where anything else. Okay, so you see the construction methods, the primary containment, I told you, pre-stressed concrete. This is the pre-stressed systems. Steel liner thickness will be the 6 mm, and concrete wall will be 120 centimeter. Internal volume will be 64,000 meter cube. Pressure, design pressure is 4 kg by cm squared. Strength test done 4.6 kg. Okay. And then you see many people have some different thoughts that if tsunami comes or earthquake comes, how it will affect with the Kudankulam nuclear power plant. Friends, I told you, as we already got a tsunami experience in the year of 2004. 26/12/2004, we have the tsunami at our Tamil Nadu. Many places has been hit. You see the Kudankulam, you see the tsunami level up to 2.5 meter height waves has been, we have seen. Whereas our Kudankulam design based is 5.44, whereas our pump house kept in plus 7.65, and our turbine is 8.1 meter. Our reactor building starts below the basement from plus 8.7 meter, and the DG, diesel generator, will be plus 9.3, and then switchyard will be plus 13. What I mean to say, even worse tsunami than the 2004 comes also. Kudankulam will not have any such worse condition. It will be in safe almost, I tell you. And I told you the outer containment will be stopped by, you see, Kudankulam especially, if the airplane 20 ton mass with 200 miles per second speed, one missile or aircraft comes and hit the reactor, this only get damaged. Reactor will be very safe. And then floods and the hurricanes, water sport, or shock waves, or seismic impact up to earth, nothing will damage our reactor. That much heavy concrete, heavy construction has been done our Indian scientists. And one more thing, marine life protection. So people will also think that the fishes will be come to the condenser area, which will then the fishermen will not get fish in that area. That is also the wrong thing. Here you see the fish, many crores rupees we have spent, and we done this fish protection facility. So when the fish comes, this area, we kept one mesh. Through this, the big fishes will go outside. The small fish still enter here. Then we are making one bubble systems. So continuous bubble will be made from the bottom side. Through these bubbles, fishes are going to top naturally, and then we are getting water from the bottom side. So more than 99.9% fishes will not come to the condenser area. By this, we are giving the life of fishermen also. Okay. And one more thing I want to tell you. The desalination plant we are keeping in plant site as well as township. Okay. Because we are making the water from seawater only. Seawater, we are taking it, we are purifying through the, you need that reverse osmosis method. We are making the seawater to the good water, and then we are using it. Okay, there are capacity of 4 into 106 meter cube per hour domestic water. We are taking the plant site and township. Okay, so this I want to give some nuclear our reactors construction site. Construction, how we have done it. You see here, sir. Before start the work, just you imagine, my dear friends, Kudankulam will be look like this. Kudankulam is sea like this. This is a bare land. You see you see here the bare lands. The sea is there. Just we have got the approval from the 1988 onwards. First approval we have got it. Then the Russia get breaks, and then 10 years we could not able to further proceed. Then 2001 only we have got the MOU, mutual of understanding. Then we have started the excavation October 2001. Okay, the below 8.39. Then 31 March 2002. As of you just today also 31 March. So like that you just imagine near about 21 years or 20 years, 21 years. So we have started the first pour of concrete. The first pour of concrete, this is a huge one. We are going to start. Then 2005, how the monument has been built, and you see the main control room in our Kudankulam nuclear project. We have the mini port, the lot of equipment. Because one thing I want to tell you from the beginning, I forgot to tell you, sorry for that. Our Kudankulam nuclear power project is the Indo-Russian project. Whatever the unit we are using it through Indo-Russian project. The design equipment has been supplied by Russia, and construction, operation and maintenance done by our Indian scientists. So you see here, all the equipment came from Russia that we are keeping here, and we are assembling it, and we are doing it. Okay, this is the turbine generator. Okay, this is the HP, that is high pressure turbine, and then 3 low pressure turbine. This is a generator, and this is the exciters. There are from right side to left if you go. Okay, this is the turbine generator. And then reactor pressure vessel. This is the RPV, what I told you. Reactor pressure vessel, RPV. This is the bottom side, you see 4 inlet, and top side you see 4 outlet. Okay, when we erected in the unit reactor building, this picture has been taken place. And then after completing this is the, I told you, 31.7 meter elevation. After completing this RPV erection, this is the fuel pool. Left side you can see the fuel pool. This is the fresh fuel as well as the spent fuel. We keep it here after completing the work. Then this is a fueling machine. Okay, this machine only will take the fuel and kept inside the RPV. Everything will be done by automatic. Okay, this is the reactor cavity, and this is the core barrel as well as, because whenever you want to, after every year we have to replace 1/3 of the fuel. Okay. So 1/3 of I already told you 163 fuel assembly kept inside this one, and 1/3 of the fuel, that means around 55, will be replaced by the old one to new one. This is the thing. 300 days full capacity it will run, and it is a shutdown replacement method. Okay. And you see now of Kudankulam look like this. Okay. So let us have the choice of clean and green energy. Welcome to the world of nuclear power. So from this, I want to conclude my thing. And before concluding, just you may have a lot of ideas about this Kudankulam nuclear power project. If you have any doubts, if you have anything, if you want to ask me, you can very well to ask me. Now I am able to give you question section. Yes.
Madam, mic unmute பண்ணிட்டு பேசுங்க.
Thank you, sir, for your excellent presentation. We got positive responses from our participants' side.
Okay. Okay.
On behalf of our organization, we would like to give an appreciation letter. Kindly accept it, sir.
Okay. Okay. Thank you.
It is sent to your mail, sir.
Okay. Thank you. Thank you very much. Any doubts
And
you have
some
from the lecturer
questions,
side? Any questions?
some questions in the chat boxes, sir.
Okay. Chat box, some questions are there. I have not seen.
So 1 neutron in the nuclear chain reaction, how can you maintain 1 neutron in the reactor?
Okay. I told you the uranium-235, uranium-234, uranium-238. This is the three will be mingled together. If you take the uranium ore, all the three will be combined. So out of which 0.7% only uranium-235, remaining 99.3% uranium-238. This uranium-235 only the fission fuel, and 233 fertile atom. Okay, this 235 only will hit the neutron. When the neutron hit the uranium-235, it only split. I told you the chemical reaction also. Uranium-235, 92 uranium-235 plus 1 neutron gives xenon, krypton, boron plus 2.5 neutron plus 200 million electric volt heat plus small amount of radiation. Out of which the heat has been taken away. For that only we are doing everything. So the heat has been taken, carry out. Remaining is 2.5 neutron. Out of which we want 1 neutron to maintain the chain reaction. 1 neutron if hit the another atom, again 2.5 will come. Again 1 is required for maintaining the chain reaction. So extra 1.5 neutron we have to observe. So the water, the control rods, we are using the boron rods. As far as the water I told you, light water, there are also some boron mixed water that is there. 4 to 16% boron will be mixed in this water. So that water will just absorb the extra neutrons available inside the reactor core. So always it will maintain 1 neutron available to maintain the chain reaction. That is why we are called, when K is equal to 1, the available neutrons from the next generation of the neutrons for maintaining the chain reaction. The K is equal to 1. When the K is equal to 1, that is called criticality. When the K is equal to more than 1, it is called supercriticality. When the K is equal to less than 1, it is called subcriticality. So we have to maintain always 1 neutron available to maintain the chain reaction. We are doing the control rods and what I told you, the boron rods. We are using always 1 available inside the reactor to maintain the chain reaction. If I want to shut down the reactor, the top control rods, most of them, we release it through the this thing, self-energized. All the rod will come down, it absorbs nearby neutrons, and the neutron available is less than 1, the plant will get shut down. Okay, we are never maintaining more than 1 because that is called supercriticality. We are never allowing it. So always we are using 1 or less than 1. Okay, less than 1 is called that is called shutdown. If I want to put shutdown, just drop the rods. Rod will come down. It absorbs all the neutrons. Neutron are available to not available to maintain the chain reaction. then the plant will get shut down. So that one neutron comes, again hit the another atom. So out of 2.5, 1.5 will be absorbed by the boron rods, and always it will allow 1 neutron available to maintain the chain reaction. This is what we are doing it. Understand, ma'am?
Okay, sir. Okay, sir. Sir, one more question.
Yes.
Since waste disposal is expensive and local thermal pollution is more, what measures taken on this?
Very good. If you are asking, then only I can able to give many things. Okay. Here, I will tell you. I am just showing some. Sorry. I will tell you. I will show some pictures about the things. You can see. One minute. Huh? Have you seen the picture waste management, ma'am?
Yes, sir. Yes, sir. Yes, sir.
You have seen waste management.
Yes, yes, sir. Yes, sir.
Okay. I will explain, because normally many slides we are having it. So now my topic has given is only the principle how reactor has been produced and what is the safety features. That is why I only kept that much. Okay, now you asked about the waste. Just I will show 2-3 slides further. This is the waste management. Every unit we are having the waste management systems in nuclear power plant. The waste, what you are designing the waste. Okay, you see here, uranium, I told you, uranium 235, 238. I told you, if you take 1000 kilogram, out of which uranium 235 is only 35 kilogram, whereas 238 is 965, as I already told you. Okay, this is the fresh fuel. Whereas the spent fuel, after completing the work, you see, out of which the uranium 235 again will be same, will be there. Then only the activated production will be 13 kg out of 1 ton. Okay, the fission product again it will be 34 kg. Okay, this is the 13 kg only will become the waste in the fuel itself. Okay, that will be very easy. We are making it a process, and then we have to remove that one. Not in here. The trombe where the waste management systems are there. There we will do. Okay, next one you see the other waste apart from the fuel. Fuel, I told you, fuel is not a waste. It is a work, because uranium 235 and the remaining 238 will become plutonium. That plutonium we are using in the phosphor reactor. So fuel is not a waste. That you first understand. Next, then what is waste? Waste is normally what happens when we are going inside the reactor for maintenance. Operational maintenance is always there. So that type of thing, solid and liquid and semi-solid. There are 3 types of waste we are gathering. Okay, for example, if you are going to maintain a pump which is having leak, if we found that 2-3 bolt has broken, so that broken bolt has been replaced, even though the broken bolt maybe have the radiated and contaminated, so we cannot throw out of it. So we collected in a pot where the nuclear solid waste, like that water spillage is there. That water we are collected into a liquid nuclear waste. And then any grease or any semi-solid things waste found, that will be semi-solid. Like that 3 type of waste we are collecting inside the reactor building, and there we are having one. Every reactor, every unit will have the waste management system, waste management building. There the solid waste has been reduced by its volume, and then as I told you here, the VIP metallic melter, and then ceramic melter, the cold crucible, like that there are facilities are available. There we are volume reduced, and then step 2, the interim storage, where vitrified water for 25 to 30 years we keep under the containment overpack and solid storage surveillance facility overpack, and then final 3rd stage disposal, deep radiology, ground disparity lab, and conceptual geology. Everything will be watched full the life cycles. So this type of waste management we are using it. So this is about the waste management system, what we are doing it in not only Kudankulam, every nuclear power plant in India. Ma'am,
Okay, sir.
any more questions?
Thank you, sir. And okay, sir. Thank you, sir. Thank you so much, sir.
Thank you. If you have any further queries, definitely you can ask me through mail so that I can give in detail to mail you, ma'am. Not only you, any of the faculties or any your students will have doubts in future, they can contact me at any time.
Sure,
Okay.
sir.
Thank you very much. So I am finally given thanks to you, your M.G.R. University, and all the faculties, especially this program has been done the requesting of Nitya. So I am my special thanks to Nitya also. Okay, thank you very much, ma'am. Anything else you want to add?
No, sir. No, sir. Thank you, sir. Thank you so
Thank you
much.
very much. Can I
Thank
close
you,
it?
sir. Okay, sir. Okay, sir.
Okay, thank you very much.
Thank you. Now I call upon Dr. R. Lavanya, Assistant Professor, Department of Chemistry, to propose a vote of thanks.
Good evening, everyone. I am Dr. Lavanya. Taken this opportunity to propose a vote of thanks on behalf of the organizing team. I would like to take this opportunity to place on record our hearty thanks to our Honorable Chancellor Thiru A.C. Shanmugam, Honorable President Engineer A.C.S. Arun Kumar, and all higher officials of our esteemed institution. Thank you, sir. I thank today's resource person, Dr. Anandan, Scientific Officer E, for sharing his knowledge and experience regarding nuclear energy. Thank you, sir. I thank Joint Registrar Phase 2, Dr. S. Ramalingam, Dean Dr. S. Manivanan, who always supported and behind us for the success of our campus activities. Thank you, sir. Deputy Dean Academic Dr. A.R. Arunachalam and Deputy Dean Administration Mr. K. Sendil Kumar, Dean Chemistry Dr. P. Udayakala, and HOD Dr. S. Valliyamai for their continuous encouragement and support. Thank you, sir, and thank you, madam. I thank all my colleagues for their support towards the success of the program. Thank you all. I thank Mr. Ganesh Babu, System Admin, for rendering technical support throughout the program. Thank you, sir. I extend my sincere thanks to all the participants for utilizing this opportunity. Thank you all.
Ma'am, unmute பண்ணி பேசுங்க.
Thank you, ma'am.
Dr.M.G.R. Educational and Research Institute, University, Mother of all Chennai.